Section 4.6, we're going to do just a lot of real-life applications. Some of these you may find quite interesting, but the title is just modeling with exponential and logarithmic functions. So some of the formulas you're going to see are going to look familiar. Maybe some of the variables are changed a little bit, but we may also be solving for different values than what we've seen in previous examples. So our first example here is we're going to go back to what we were doing at the very beginning of the semester here, which was to solve for an indicated variable, and just gives us work with or practicing with the exponential functions that we've been working with so far. But instead of getting an actual answer, it's just solving for one variable in terms of another. So let's take a look at part A of example 1. Here we're given this formula: P is equal to 100 times e to the kx, kx is all in the exponent, minus 100. We want to solve for x. So we want to get this x that's in the exponent by itself. So the first thing we're going to do, I'm just going to rewrite the equation here. And what's nice is it kind of gives you where this could be applied, and this is used in geology, this formula. So I want to take this constant, this minus 100, and just add it to both sides. So now we just get P plus 100 is going to equal 100 times e to the kx. Now I have to get rid of this 100 that's out in front, so I'm going to divide both sides by it. So we get P plus 100 divided by 100 is going to equal e to the kx. So now we have to get the exponent to come down. So how do you think we're going to do that? We're going to take, we'll just use the natural log for these examples. We're going to take the natural log of both sides. So we have the natural log of this left side, this quantity here. It's going to equal the natural log of e to the kx. So two things can happen. We know natural log and e cancel out, and we're just left with kx, or we could just bring down the kx in front, and then the natural log of e turns into 1. But either way, our next step is just to show this. This will just equal kx. And now to get x by itself, we have to divide both sides by k. So I'm just going to flip this around. We're going to say x is going to equal the natural log of this fraction all over k. Or to make it look maybe a little bit nicer, we can expand the numerator. That's why we learned those properties. So this becomes the natural log of the quantity p plus 100. And since I'm dividing this here, I'm going to subtract the natural log of 100. And then this will all be over k. So we'll try another example. This formula is actually used in astronomy. But we're going to solve this for d. So we have L is equal to 8.8 plus 5.1 log d, and we want to solve this for d. So if you want to pause the video and give this a try, you can. If not, let's go through the steps. Again, I'm just going to rewrite the formula. We're just going to start with this constant here, 8.8. I'm going to subtract it from both sides, so we get L minus 8.8. is going to equal 5.1 times log d. Next, we have to get rid of the 5.1. We're going to divide both sides by, because right now it's 5.1 times log d. So we're going to have L minus 8.8 all over 5.1 is going to equal log d. Now, if you notice the way it's written here with log, it's technically that base 10, right? So in order to get rid of a log base 10, we can just use a power of 10 on both sides, or we could just rewrite this exponentially. So we could just have 10 to this fraction, L minus 8.8 over 5.1 is going to equal d. And we could leave it just like that, but I'll rewrite it this way. D is going to equal 10 to the L minus 8.8. We could even write it like this in parentheses, divided by 5.1. Now, in the upcoming examples, there's going to be a little bit to write down, so please take the time, just pause the video at the very beginning to copy down the problem. So here we're looking at something that should look very familiar, an investment problem, but what we're going to be asked to find is a little different than what we were asked in previous sections. So here we're going to suppose that $15,000 is invested, and at the end of 3 years, the value of the account is $19,356.92. we're going to use this formula, A equals P times e to the RT, to determine the average rate of return, R, so we need to solve this for R, under continuous compounding. So that's why we're using this formula. So the value we're going to put in for A is going to be this 19,000 number. That's going to equal, the P is our 15,000. And then we'll have E, and we're looking at 3 years, so we'll have R times 3, or we'll just say 3R. So how do we start to solve for R? Kind of like our very first example, we want to divide both sides by 15,000. And I just want to leave this as a fraction right now. I do not want to turn this into decimal, so I'm just going to leave this 19,356.92 divided by 15,000 is going to equal e to the 3r. So now what do you think we have to do to both sides? If you're thinking take the natural log, you're correct. So we're going to have natural log, again, of this fraction. And then what we'll have on the right side here, because we took the natural log, again, natural log and e are inverses, so we'll just have 3r. I'm just going to flip this around. We'll have 3r is equal to the natural log of this value. And then all we have to do is divide by 3. So that would be the exact value. And then just take the time to type this into the calculator. We'll say r is approximately. So if you want to pause the video and carefully type this in. We should get a 0.085, which would translate into 8.5%. So the average rate of return is 8.5%. Right, this next example has 3 parts. And here we're actually looking at population growth. So this starts by saying just on January 1st, 2020, the population of California was approximately 34 million. Going back to 2010, January 1st of 2010, the population was 37.3 million. For part A, we want to write a function of this form, P of t is equal, this is representing like the initial population whenever you see this little subscript of 0. So the initial population times e to the kt. This is nothing different than a equals p times e to the rt. Like I said, just different variables. And this is used to represent the population of California, P of t, in the millions, t years after January 1st of 2000. We're going to round k to 5 decimal places. So we're going to start off, just rewrite the formula here. Again, if you need time to copy this down, pause the video. All right, so we know the initial population, actually let me go back up, that wasn't 2020, that was the year 2000. So in the year 2000, the initial population here was 34 million. So we're going to say P of t is going to equal 34 times e to the kt. But we want to know what k is. So we're also going to set this up in order to find that. We know in 10 years, the population is now 37.3 million. So now if I put P of t to be the 37.3, I'm going to have it, it's going to equal 34 e, and that's going to be t is 10, so we'll have 10k. And now I can solve this for k. So I'm going to divide 37.3 by 34. And that's going to equal e to the 10k. I'm going to continue over here. And just like the last problem, we're going to take the natural log of both sides. Again, I do not want to get this value yet. If we round somewhere in the middle of our problem and then we round again at the end, our answer is going to be a little off. So we don't want to do any rounding until the very end. So now we just have the natural log 37.3 over 34 is now just going to equal 10k. So k is going to equal this natural log value divided by 10. And we'll get our calculators here and say that this is approximately 0.00926. So now we could say that P of t is going to equal 34. Now that we have a value for k, that's like finding our average rate of return. So it's e to this 0.00926 t. And now this will allow us to find the population in any year. But that's what we were looking for part A. All right, for question B, they want us to use the function from part A to predict the population on January 1st of 2018. So remember, t is the number of years after the year 2000. So in this case, t is going to be 18. So now we can say, start with P of t is equal to 34 e to this 0.00926. So this will now become P of 18 is going to equal 34 times e to this 0.00926 times 18, and all we have to do is calculate that. It says round to one decimal place. And we should get 40.2. So remember, this would say in the year 2018, the population would be about 40.2 million. And it's approximately. Okay, now for part C, we're going to use the same function to determine the year during which the population of California will be twice the value from the year 2000. So in 2000 was 34 million, so we're going to go back. I'm just going to rewrite the formula we're using again. So if we double 34, that's going to give us 68. We're going to divide both sides by 34, so 68 divided by 34 simplifies nice. Since it's double, we're just going to get 2. Take the natural log of each side. Now, even though we know this is going to cancel, I still want you guys to show this step. Show you're taking the natural log of each side. So now we just get the natural log of 2 is going to equal this 0.00926t. So now t is just going to equal the natural log of 2 divided by this decimal. That's the exact value, and then this is approximately, again, if you want to pause the video to type that in. We should be getting 74.85. So this means that the population, just abbreviate here, will double. So that's almost 75 years after the year 2000. So we'll just say by the end of the year 2074. So the population will double toward the end of the year 2074 if the trend continues. Okay, let's take a look at our next example. This now is going to be an example of writing an exponential function with base e. So again, pause the video to copy down example A. And in this example, it tells us the population P of t of a culture of bacteria, it's just like a sample of bacteria, is given by P of t is equal to 5,000 times 2 to the t divided by 4, where t is the time in hours after the culture was started. We're going to write the rule for this function using base e. So again, pause the video if you need more time to copy that down. So one thing we're going to make a note of is 2 to the t over 4 is the same as saying 2 to the t and then to the 1/4, just using laws of exponents here. And if we need to get this in base e, we can now turn this into e to the natural log of 2 times t and this will be to the 1/4. So I'm going to go ahead and explain this. We're applying the property here that e to the natural log of b times t is just equal to b to the power of t. Because we could think of it like this. So this will just give us b, and this t still stays as an exponent. So 2 to the t, we could rewrite this as e to the natural log of 2, because that will just drop down and give us a 2, but the t will still stay as an exponent. And now we can rewrite this as e to the natural log of 2 divided by 4, bringing this inside and just switching the 1/4 and the t out. So 2 to the t over 4 ultimately turns into e to the natural log of 2 over 4, and then times t. Now we could say that P of t is going to equal, start with this 5,000 times 2 to the 1/4 is going to equal 5,000 times e to this natural log of 2 divided by 4. Keep the natural log of 2 in parentheses though, to the t. And now we're actually going to calculate natural log of 2 divided by 4. So it becomes 5,000 times e to the 0.17329 times t. All right, for part B, we want to find the population after 12 hours using both forms of the function from part A. So we'll say form 1, which was the form that was given to us. So that's the P of t is equal to 5,000 times 2 to the t over 4. So we'll have P of 12. Times 2, this will be 12 over 4, which would just be 3. So it's 5,000 times 8, because that will be 2 cubed, and that gives us 40,000. All right, so form 2, this was P of t is equal to 5,000 times e to the 0.17329 times t. So now we'll do P of 12 this way. And we also get 40,000. But this is approximately 40,000, where the other one came out to equal exactly 40,000. Okay, and just 2 more examples. Okay, this next one deals with exponential decay. Again, pause the video to copy this down. In part A, it says carbon-14 has a half-life of 5,730 years. We want to write a model of the form Q of t So notice this is still that like a equals p times e to the rt, but because it's exponential decay, our rate is decreasing, so we have a negative k times t. And this represents the amount Q of T of carbon-14 remaining after T years if no additional carbon is ingested. So we're going to kind of do the same thing we did in the last two examples ago. We have to find out what K is. So we're going to start with Q of T equals this initial value, e to the negative kt. Now we don't have an initial amount, but we're trying to show that it's half that's remaining there. So whatever initial amount we start off with, we know that this Q of T is going to be half of that initial amount. And it takes 5,730 years to become half of this amount. So it's e to the negative k times 5730. So now what we could do is divide both sides by this q sub 0, or q naught, that's right here, the initial amount. So those just go away. And we have 1/2 is equal to e to the negative k times 5730. And then we'll take the natural log of both sides. And we'll continue this over here. So this natural log and e will cancel. So I'm just going to rewrite it this way. Negative k times 5730 is going to equal the natural log of 1/2. So k, I'm going to divide both sides by negative 5730, is going to equal natural log of 1/2. And actually, I'll just put the negative. I could move the negative, and then over 5730. So then k is approximately, we're going to take this one out pretty far, 0.000121. So our model now is Q of T is going to equal this Q naught times E, and because K had a negative sign up here, now we're going to go back to a negative 0.000121 times T. Again, pause the video to copy down example B. I think this example is pretty cool. An archaeologist uncovers human remains at an ancient Roman burial site and finds that 76.6% of the carbon-14 still remains in the bone. How old is the bone? We're going to round to the nearest 100 years. So because it's a 76.6% that remains, it hasn't gone down to a full half yet. So we know a full 5,730 years haven't passed yet. So we know it's not going to be that old. But we are going to start 76.6%. We're going to turn into a true decimal, so it's going to become a 0.766 of this initial amount is going to equal the initial amount times e to the negative 0.000121 t. So again, I can divide both sides by whatever number the initial amount is. We don't care. It's just gone. It divides out. So we have a 0.766 is equal to e to this negative decimal here, 121 t. We'll take the natural log of both sides. And again, natural log of e will cancel. I'm going to rewrite it this way. Negative 0.000121 t is going to equal natural log of 0.766. I'll divide both sides by this decimal here. So t is first going to equal the natural log of 0.766 divided by negative 0.000121. And this will be approximately 2,200. Not too bad. All right, and we just have one more example. It will also have 3 parts. All right, so this is another way that we're going to model the population growth of California, P of T in the millions. One of the answers we get, we're actually going to go back and compare it to what we got. I think that was example 3. So this population growth can be approximated by this logistic growth function. P of T is equal to 95.2 divided by 1 plus 1.8 times e to the negative 0.018 times t, where t is a number of years since the year 2000. So we're going to determine the population in the year 2000. So if t is the number of years since the year 2000, for this problem, this means t, no years have passed since 2000, so t is going to be 0. So I'm just going to rewrite the formula here. We're just going to substitute in 0. So P of 0 is going to become 95.2 divided by 1 plus 1.8 e to this negative 0.018 times 0. Well, this becomes e to the 0, and if you guys recall, anything to the 0 power is 1, so we just get 95.2 over 1 plus 1.8. And we'll continue this over here. This means P of 0 is going to equal 34. And if you recall, the information that was given to us in example 3a told us that the population in the year 2000 was approximately 34 million. All right, example B, determine the required time for the population to double from its value in 2000, and we're also going to go compare this with the result from example 3C. So starting off with this, we know we can start with P of T to equal 68, and that's going to equal that 95.2 over 1 plus 1.8 times e to the negative 0.018t. So what I'm going to do, I'm going to multiply both sides by this denominator. So we're going to get 68 times this denominator quantity. And then that's going to equal 95.2. And then we'll just switch it around. Now we'll divide both sides by 68. Not 9.52, but 95.2. And actually with this, if we divide it, we get a nice terminating decimal. We could just put that as 1.4. 95.2 divided by 68. Now we can subtract a 1, so we get 1.8 e to the negative 0.018t, which is going to equal a 0.4. Next, we'll divide both sides by 1.8. This I'll just leave as a fraction. We'll take the natural log of both sides. Continue this over here. Natural log of e is just going to turn into a 1 there, so we just get the exponent that drops down, and we'll divide this natural log by this decimal. So t is going to equal the natural log 0.4 over 1.8 divided by a negative 0.018. And this will give us approximately 83.6. So this tells us that the population will double in approximately 83.6 years. So if we go back to example 3, C, we were told, or we found out, the population would double in approximately almost 75 years or 74. So this is 9 years after that. And we can kind of take a look at, when we go to answer the next question, why there could be a difference here. And then the last part is, what is the limiting value of the population of California under this model? So a limiting value just tells us as T keeps increasing without bound. So if we take a look at this model, if T keeps growing without bound, that means this value is going to become a very large negative number. Now I'm going to go back to the property of exponents. Negative exponents really means we take the reciprocal. So this now becomes 95.2 over 1 plus 1.8. And then this really becomes times 1 over e to a positive 0.018, because e to a negative power just becomes 1 over that. So as this denominator keeps getting larger and larger now because it's positive, if we have 1 over a very large number, think about like 1 over 1,000. Because the 1,000 is in the denominator, that's actually a very small number. Now think of 1 over 100,000. That's even smaller. Or 1 over 1,000,000. That's even smaller yet. So the larger the denominator gets, this number is going to go to 0. So then we really just get 0 times the 1.8. This whole thing will just go to 0, and we're left with 95.2 over 1. So we say this is a limiting value because of the limited resources to sustain a large human population. So it is going to be limited. It can't keep increasing. It is going to be limited because there's only so many resources. So if we go back to the answer for part B, the logistic growth model approaches a limiting population. So that's why this is going to look to be 9 years later than what we saw in example C, because example C assumes that a trend is going to continue. So it's graphically, it's going to be a slightly different graph than this logistic model, which is kind of more applicable to this type of situation. All right, so those were all the examples from section 4.6. The activity 5 that I'm going to give you guys is going to focus on sections 4.4 and 4.5. This I just wanted to go over so you can get through ALEKS, and then we'll practice some more problems after Thanksgiving break.